Hello, everybody. Today I'll be covering electric fields for physics A levels. It's very similar to gravitational fields and it's not really that difficult. So let's get started. An electric field is a region where a charged body experiences a force. Again, these charges I'm referring to point charges where they have a small positive charge with no mass. Coulomb's law, any 2 point charges exert any 2 point charges exert an electrical force on each other that is proportional to the product of their charges and inversely proportional to the distance between them. It's represented by these equations over here. As you can see, that the gravitational force is always attractive. However, for electric force, it can be attractive or repulsive. And K over here is a constant of proportionality. It's represented by 1 over 4 pi epsilon not epsilon, which is also known as the permittivity of free space, which has a value as 8.85 times 10 raised to the negative 12, and K has an experimental value of 9.0 times 10 to the power of 9. You can memorize these as any way as you like. You can memorize it as such, or you can substitute K, this value inside. Don't worry about memorizing these values because they'll be given in your data booklet. Electric field strength. It is a force per unit positive charge at a point, and it's a vector where E equals to F over Q. Using the formula that we derived earlier, we can it's divided by Q1 or the other charge. It can be any charge, honestly, which will give you Q1 times K over R squared. Next up, we have electric potential. Its definition is the work done per unit positive charge to bring that charge from infinity to that point. And the equation is as such. Q1 over 4 pi epsilon 4 pi times permittivity of space times R, and the graphs look as such. If it's a negative charge, it will have a negative value, hence it's reflected about the x-axis, and it decreases in potential as the distance decreases. And this is for the positive test charge, hence it's above the x-axis, as Q1 would have a positive charge, and as the distance decreases, the potential increases. So you can think of it as a diagram, and you have a large positive charge over here. If the test charge was positive, as it approaches closer and closer, the potential will increase because a potential will increase. And if it's a negative, and we know charges move down a potential gradient, right? So this shows that it's a positive test charge because the charge would like to move from high potential to low potential. That shows that the distance it'd like to go from close to far, hence the repulsion is taking place. However, if it was a negative charge, and like I said, charges move from high potential to low potential, it will move down this graph, which shows that it's going from far away to closer, hence its attraction. That's a way you can think about it and analyze the graphs. Equipotential and charges in a conductor. Equipotential points are points where the electrical potential is the same. Thus, no work is done in moving along a point of an equipotential point or line, because work done is change in potential times charge. And if there's no change in potential, there's no work done. Charges in a conductor are equally spread along the surface, and they do not move inside the point charge. This is somewhat related to Gauss theorem. However, you don't need to know that for A levels, but you just need to know that the charges in the conductor do not move inside the conductor, and they're equally spread along the surface. Thus, the electric field strength is 0 or constant inside the conductor. Potential gradient, the definition is change in potential per meter at that point within an electric field. So like I said, we can analyze these graphs and you can get a better understanding. So E equals to negative V over D, the negative gradient of the voltage distance graph, where E is the electric field strength. Like I said, it's negative because the charge is moving away. So the force is opposite the direction moved by the graph or by the charge. So as you can see, as you get closer, the force is getting larger in the opposite direction, because repulsion, using the Coulomb's law, like we've seen over here, it's inversely proportional to R squared. So as you get closer, the force increases, as the distance decreases, but the direction of force is opposite the change in potential gradient. So that's one intuitive way to look at it, and it has helped me. The units is joules per coulomb per meter or volts per meter. So now let's look at graphs for oppositely charged objects. So the electric field strength will decrease, will have a U-shaped graph, and the voltage will have like a S or a S-shaped graph, or like a curved graph that cuts the x-axis. And next we have graphs for like charges. This is for negative charges. For two positive charges, this will be flipped upwards, and it'll be like a smile. This is a frown. It'll be a smile above the x-axis, and the electric field strength will have a S-shaped graph. So now let's look at similarities and differences between gravitational and electric fields. So the force is inversely similar. First similarity is that the force is inversely proportional to the square of the distance between the two masses or the two charges. Negative sign for gravitational fields. So remember that the force is always attractive for gravitational fields. However, for electric fields, it can be repulsive too. The potential for both is inversely proportional to the distance, 1 over r squared. And the field strength for both is the force divided by the property that it represents. Differences are the gravitational fields are always attractive, while electric fields can be attractive or repulsive. Gravitational fields affect mass, while electric fields affect charge. So we've come to the end of electric fields. I hope you understood electric and gravitational fields completely. If you have any suggestions or you enjoyed the content that we're putting out, please give a like and leave your ideas in the comments. I'd love to take a look at them. Thank you and goodbye.